Hey, yo. Share screen real quick. So today we're going to be going over lab design here. This is a dynamics lab, meaning we're dealing with forces, and we'd like to find properties of things related to forces and Newton's second law, which is the sum of net forces is equal to mass times acceleration, or net force is proportional to acceleration. Force causes acceleration, and mass is a resistivity to acceleration. All those are equivalent. So we're going to be doing a lab design here to talk about the springs that are attached to this apparatus. So we're going to be doing a cool experiment here. Personally, I think it's cool. That's talking about the using like Springs force Hooke's law, F equals kx. This experiment allows you to find 3 unknown variables, which is really cool, actually, I think. So basically what the experiment is we have this this rod almost right here that has a larger base at the end of it, and there's a hook on the rod, and this hook is attached to 2 springs that are both hanging from the ceiling like this. And then when you release that, and these springs have varying strengths also. If you release the rod, it's going to move a little bit to the right, a little bit to the left, depending on the relative strengths of the spring. It's going to oscillate a little bit. Ideally, when there's no air resistance involved, it would keep on oscillating, and you wouldn't be able to do anything with the net force equaling 0 on the object. So what you do have to do is you have to sort of talk about something that people aren't used to talking about. Oh, someone just joined the stream. Hey, Ari. So I'll briefly go over the experiment again. What we have here is we have a rod attached to 2 springs via a hook, and then we have N rings on the rod, and we're releasing it from the ceiling, already being attached to 2 springs. So basically what will happen is it'll oscillate, and then it comes to rest eventually because of air resistance. And once the rod comes to rest, we can analyze the forces acting on it. And although we're relying on air resistance to be a thing, when the rod comes to rest, air resistance is no longer a thing because it's not moving, so air's not pushing on the rod unequally. Obviously, or not obviously, but there is air particles hitting the rod at a continuous rate based off of the temperature of the surroundings, but they're hitting equally, so their collisions, or the effects from their collisions, can't stop because they're hitting equally on both sides. Whereas when it's moving, there's an unequal hit, so there's a force of air resistance. But now the speed is 0 because it's no longer oscillating, because air resistance brought it down to a 0 speed. So we don't have to think about air resistance anymore, which is nice. So this experiment allows you to find 3 variables. We're talking about N rings of mass mu per ring. This is not coefficient of friction. This is just using a Greek letter for 1 mass and a Latin letter for 1 mass. You might see capital M and lowercase m. You might see M1, M2, but I'm choosing mu just so the letters are more distinct. And from here, you could find, if you know the mass mu, if you know the variable mu, you can find mass m, k1, and k2 with 1 experiment, just by measuring the h value right there, where it's going to fall, or the displacement, the vertical displacement of the rod from the ceiling after it's done oscillating, which is the equilibrium displacement, and L1, the distance, if you think of like a axis splitting through the middle of the rod, the distance from that axis to the first spring on the ceiling, and same case analogously with the second distance with the second spring. So the first step we need to think about here is we need to think about what the spring force is, the magnitude of the spring force, right? We do know from Hooke's law that the force on a spring is F equals kx, or rather, more properly, F equals k delta x, meaning the force on a spring is equal to the spring constant times the displacement from the equilibrium position. So when we think about when the experiment starts, these springs are the springs are almost. We're considering what happens when they're we're holding the block up. So the springs are in equilibrium position. What happens when the springs are in the equilibrium position? There's kind of an issue here when you think about this, because when you're holding it up, there is friction that's holding the thing from not moving back and forth. Because when you're moving back and forth, the springs are pulling on the springs are both pulling on the rod that's being held by the hook. So it's sort of moving back and forth if you're not accounting for it. So if you hold it up and touch the ceiling with it, and there's no friction at all, then yes, the two forces of the springs are equal to each other when it's up, pushing at the ceiling. But otherwise, there's a force of friction that's affecting the system depending on how hard you're pushing the rod. So we have to make some assumptions here, which will be important in finding an actual analytic solution to what we're trying to solve. So what we're going to assume is that for spring 2, the equilibrium position is just equal to this length. We're assuming a negligible horizontal or oscillations in the rod, which means that the spring strengths are approximately equal, which makes a little bit of sense. In a lab, they're not going to be order of magnitudes apart. So the equilibrium position for spring 2 is just going to be L2. We're assuming this thing falls straight down, and we're assuming the spring is perfectly laid flat. And for the same reason, for spring 1, the equilibrium position, EQX, mean equilibrium X, equilibrium position, is equal to L1. So next step is we have to find how much the spring is actually stretched, or the distance from the string or whatever is holding the spring onto the rod or connecting the two. And we use Pythagorean theorem for this. So when we're looking at this one right here, we have a height, we have L2, and then we have some unknown distance right here, which is the length of the spring that we're trying to calculate. So this length of the spring, we'll call it R1, is going to be square root of h squared plus L2 squared. Someone else just joined. Hi, Matt. This is the apparatus that we're dealing with right now, Matt, or that I'm dealing with. No one else is in the stream. But basically, we're just, if you can get the diagram, we're just releasing it from the ceiling and seeing how the system is affected. And from there, we can find an experiment to find the two spring constants and the mass of the rod, knowing the mass of the rings. And similarly, for the same reasons, we have R2 is equal to square root h, that should be L1 squared right there. And then we have R2 is equal to square root h squared plus L2 squared. And we have the equilibrium position, and we also have R1. So the displacement for each of them, I'm going to be writing delta x sub I, just so I don't have to write down two equations. Delta x sub I means either spring 1 or spring 2. So this is going to be equal to square root of h squared. That's hilarious, actually, that I just wrote h bar. I'm in an intro quantum class, and h bar is a very common constant, so that's really funny that I instinctively wrote that down. Minus Li, based off of the final distance the spring is stretched, minus the equilibrium position of the spring. So we now have this established, and we can now do some work. So we have to look at the horizontal component of the spring force, right? So let's look at the first spring, for example. There's a force pointing upwards like this, and then we'll write down this extra step as well. So this means the spring force for both spring 1 and 2 is Ki, because we denoted this K1 and K2, which which means the spring constant in the first one, the spring constant in the second one, times square root h squared. I almost did the h bar thing again. Li squared, which would be better, square root minus Li. So now we have Fi, and we also have, what we need to find is we need to find an expression for the horizontal component. So this is actually going to be 1 because we're looking at spring 1. So this is also for 1. So first thing we need to do is we need to think of the angle here, right? And using just normal dynamics, we'd see Fx1 is equal to F1 times the cosine of theta. But what's the cosine of theta? The cosine of theta is it's adjacent over hypotenuse, right? So we also have in this triangle, this angle is the same as this angle. We have adjacent over hypotenuse. The adjacent side is just L1. So this is F1 over L1 over the hypotenuse, which is what we got over here, h squared plus L1 squared, square root of that. So L1 squared plus h squared. And now we can substitute this expression in, and we get F1 is K1 times, let's see, we have K1, yeah, times L1, because this factor right here, times square root of L1 squared plus h squared minus Li, which is just L1, all over square root of L1 squared plus h squared. So similarly, we also have Fx2 is just this expression with a 2 in it. So that's K2 L2 square root of L2 squared plus h squared minus L1, or that's L2, not L1, divided by square root L2 squared plus h squared. So in order to get a really meaningful calculation out of this system, we have to make some assumptions here. And the assumption is that the spring goes down, like, or the mass rod goes down very far. So we have this hypotenuse right here being much greater than this L1 right here. So if this quantity, which is the length of the hypotenuse, minus this quantity, if this square root stuff is much greater than this square root stuff, we get the square root stuff approximately equaling that sum, which is a very important physical assumption we can make. So for L squared plus h squared, denote an I here because it's for both cases, minus Li, or rather this would be much greater than Li. This means that square root Li squared plus h squared minus Li is approximately equal to Li squared plus h squared. So this quantity will reduce to that, which means that this and this cancel, and we get K2L2. And it's also the same case for K1, L1. So now we have K1, L1 equals K2, L2. And the reason that is because the horizontal forces have to be equal and opposite in direction because it's not moving horizontally. So we're going to divide this over by L1. So we get this is equal to K2, L2. Well, actually, we'll just keep that relation for now. And then when we're thinking about the next one, I'm going to expand this over a little bit so we have more room to deal with stuff. We have to look at the vertical direction. And the vertical direction is just going to be the similar case where we have this F1, which is just the spring force upon spring 1, times the sine of the angle, because that's the vertical component, plus F2. Well, actually, we'll say sine theta 1 just to be explicit, plus F2 sine theta 2. And we have to think of the gravity force here. So we have n rings of mass mu per ring. So there's mass mu per ring, so the total mass is mu times n. So this is mu n times the force of gravity, because now you have a mass of all the total rings together. So you have to multiply that by the acceleration of gravity. And then you also have the mass of the rod times g. So what sine theta is sine theta is just, let's see, so we have this angle right here. So sine theta is going to be opposite over hypotenuse, which is going to be h over the hypotenuse. So now we have F1 times h over square root L1 squared plus h squared plus F2 h over square root L2 squared plus h squared equals, I'm going to factor out a g here. Actually, no, I'm not going to factor out a g here. I'll make it a little more confusing later. So we have an expression for the force, right? The force is this thing, and we found out that this reduces to k I square root h squared plus li squared. So we found out that reduces to that. So now we have F1 is k1 times the denominator. So this will just reduce to k1h. So now we have k1h plus k2h is equal to mu ng plus mg. Hey, we have another person that joined. Welcome. We're just doing a lab design here with this apparatus right here, where we measure both spring constants in one simultaneous experiment by attaching attaching rings to a rod and then letting it hang from two springs. But we also have this expression right here. So we'll see what I have prepared here. Yeah, I have prepared. Okay. So we can do either one actually. So I'm gonna substitute in for K2. So we have K2 is equal to, no, actually I'll substitute for K1. We have K1 is equal to K2, scratch that again, because I remember how I have this prepared. K2 is equal to K1 L1 over L2. So we can substitute this in for K2 right here, and we get K1H plus K2, which is just this expression, K1 L1 over L2 H is equal to mu ng plus mg. And now we can factor K1H out. So now we get K1H 1 plus L1 over L2 is equal to mu ng plus mg. So now we're going to divide everything by ng. So to get n alone, because we're solving for n, because we're going to end up graphing n as a function of the height. So now what we do next is we subtract this mg over, so we get K1H 1 plus L1 over L2 minus mg is equal to mu ng, and we're going to divide everything by mu g. So we get K1H over mu g times 1 plus L1 over L2 minus, so mg, so we're doing mg divided by mu g. This is just m over mu. Minus m over mu is equal to n. So if you really understand this exercise, you might be able to see what we're going to do with this data. So what we're going to do is we're going to, we know mu, we know g. These are both, one is something we already know, maybe by like on the designer package, we know g just because it's a fundamental constant. Well, not fundamental, but it's a constant. And then we have L1 and L2. We are assuming we know those. So we don't know K right here, we don't know M right here, and we don't know N. So what we're going to do is we're going to set up an experiment such that we can find out all of these. And if we plot, or if we put on multiple rings on the rod and we let it hang, we're going to see a graph like this. We're going to see N as a function of H. The graph is going to somewhat look like this. Right, because this is y equals mx plus b. M is positive, mu is positive, so negative m over mu is negative, so it's going to have a negative intercept, because this is like y equals mx plus b, where b is negative m over mu. So we can find the vertical intercept of whatever line of best fit we make, and from there we know the value of m over mu, and then we can divide or multiply mu over on both sides and find the value of m. So I don't have the apparatus with me, so we're gonna show you that I already made up some data points that seem to be similar in variance to what you'd see on AP, which is nice because AP will never give you a straight line. So keep in mind here when we're solving for the slope here, and I forgot to mention the slope. This is a function of h, so the slope is going to be everything that's h is being multiplied by. So the slope is equal to k1 over mu g times 1 plus L1 over L2. So we have this line of best fit here, and there's some really important points on AP that we have to think about. This technically isn't right with the assumption we made, so I'm just going to say L1 is twice L2. Because we made the assumption that the height was, or the hypotenuse was much greater than the length. So there's some important notes to be made here. What AP always wants you to do is they want you to use the entire scale of the graph. So here, when we're looking at the data points we have it varied from 0 meters to 0.6 meters. And one thing we have to do here is we have to see how many like scaling, or what our degree of scaling is here. So we're going to count the lines. We have we have 1, 2, 3, 4, 5, 6. I think I'm miscounting. I'm not including the thinner lines. 1, 2, 3. No, it's like this. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, and you can keep on counting those, and you'll get that there's 18. So we have something that's supposed to spread at 0.6 meter interval, and we have 18 slots. So we're going to use every 3 lines is 0.1 meters to fill up the entire scale. And similarly, I kind of got lucky with this graph right here. There's 6 lines and there's 6 rings, so we also need to fully fill up the vertical axis. And normally you would not include a negative part of the graph here because most of the time it's not relevant, but we actually do need to find an intercept here to find the mass of the rod. And you also have to plot your points accurately. It's kind of a given. So yeah, we're gonna draw a line of best fit here to see what our data looks like. So that's a good line of best fit. So this would be a line of best fit of the data. And from here, we can calculate a lot of things. So we have, previously, we showed that the slope is equal to K1 over mu g times 1 plus L1 over L2. So we know that, so we can, first thing we'll do here is L1 is equal to 2L2. So we substitute 2L2 into here, we get 2L2 over L2, which is just 2. So this whole thing becomes 3. So for this case specifically, it would be 3K1 over mu g. So the spring constant that we're looking for, K1, is equal to mu g times the slope divided by 3, just by algebra and showing K1. So we need to find the slope here. So we drew this line at best fit, and we're going to do rise over run. So we're going to see approximately where the line intersects some key points in the graph. And right here is a good point, a good candidate. You can use any points because it's a linear line. Or because it's linear, you can use any points you want. And where's another good candidate? We'll do right here because it intersects right at a corner. So this point right here is going to be, let's see, 2.33, 2.66. So 2.66, and at n equals 2. And at this point, we have 0.33, 0.66, or 0.033, 0.066, 0.1. So this is 0.033. This point isn't right. This is, let's see, 0.266, comma 2. And then we also have 0.033, comma -1. So to find the slope, we do rise over run. And the slope, we'll say approximately because we don't really know. This is just some data set. So the first point would be 2, the first y value, and then minus minus. So that's minus -1 over run, which is 0.266 minus 0.033. So this is going to be 3 over, pull up my calculator. By calculator, I mean phone. Minus 0.033, 0.233. I really should not have done that in my head. 0.233. And we get that this is equal to 3 divided by 0.0233, or 3 divided by 0.233, 12.876, around there. So now we plug it in to find K1. And now we have the data. We have mu is 0.002 kilograms. So we get 0.0020. G is just acceleration due to gravity, which is 9.8, times the slope, which is 12.876, divided by 3. And we get this is equal to 0.002 times 9.8. Let's hope I don't mess up and fat finger the calculator, because that'll be really embarrassing. 12.876. Get a really weak spring. We get 0.0841 with 3 sig figs, and it's a spring constant, so it's in units of newtons per meter. And then we also have the expression for the second spring constant. So L1 over L2, just by this expression, is equal to 2. So the second spring constant from this relation right here is twice this value. So we get K2 is equal to 0.168 newtons per meter. And this is consistent with the assumptions we made before, right? The assumption we made was that that hypotenuse was much, much greater than the original length between that vertical axis we talked about of symmetry and where the spring is placed in the ceiling, which means that spring constant is very weak because that means it falls down a very large distance. But what about the mass of the rod? We have to look at this intercept point here. And we have this being -1, -2, just based off the scaling we had before. So we'll say this point is approximately, well, it's definitely 0. It's definitely 0, right? This part right here, the arrow should be somewhere else, definitely. This right here, 0, and the negative value here is about -1.4. So we have, and we established earlier that the vertical intercept was equal to, what is it again? It is m over mu. So we have m is equal to mu times the intercept, which is, we're going to keep it in grams just because we don't, it's not really, it's bad to express this kind of stuff in kilograms when it's already a small mass. So we have mu is 2 grams, 2.0 grams, times the intercept, which is 1.4. So the mass of the rod is about 2.8 grams. So we've calculated 3 unknown quantities. We calculated the spring constant on spring 1, spring constant on spring 2, and the mass of the rod, which is about 2.8 grams based off of the experimental data we got, which means it's a really light rod. Do we have any questions from the people watching? Any at all? Okay. So let's see, what experiment could we talk about next, since there's plenty of time left. And I'll what's the canvas size that I set for this? 2,000 by 1,000. Canvas. So we have, well, there's other ways we could have done this experiment that would have been a lot nicer for us. So I'm going to talk about that. But it would require doing 2 different experiments. So the nice thing about this is that although it would take a longer time to set up, you would only have to have 2 graphs of data and only collect 1 set of data. So if we did like a, let's say, I'm going to copy and paste this over. Let's say we had copied it from the wrong layer. Okay. I think I got it this time. Yeah, there we go. So if we had this attached to, we'll say any arbitrary spring K, and we measured the height. For the same reasons before, we'd have, this time it would just be the height of the spring that's being stretched, right? It would just be K times H, that's the spring force, is equal to the force of gravity because the thing isn't moving, which would be mu ng plus mg. And then you have the mass as a function of the height. We'd have, or the number of rings as a function of height, we'd have mu ng is equal to kh minus mg. It's a much simpler mathematical calculation. You also don't have to make assumptions about the quantities of the system that we had to make there to make sure those 2 quantities canceled before. In this thing, we had to make this assumption right here, which allowed us to do this cancellation right here, which also made our data only approximate. So the good thing with that experiment is that we can do 1 experiment and measure 3 quantities. However, the measurements we do get are going to be approximate. So for a really fine system where we have to really think about the mass, like if you were asked to express things in like 6 significant digits for some reason, you'd have to probably do 2 separate experiments. So the great thing about this experiment is that the measurements are more precise. So 1, measurements more precise. 2, the algebra is easier, and 3, But there really isn't a third option. It's easier to set up, basically. So dividing everything by mu g, we get n is kh over mu g minus m over mu. And you get a very similar looking graph. Let's see, n versus h. You get a graph that looks like this. Again, the same graph. You'd have this vertical intercept right here, negative m over mu. And then you'd have a slope of k over mu g. So in this case, k would equal mu g times the slope. And again, there's some obvious advantages here, but if you're crunched for time, a lot of time is going to be taken up measuring the data, finding the data points, graphing the data points, calculating the slope. So in this case, if you're doing this for 2 separate springs or 3 separate springs even, you'd have to do this experiment twice. And the first experiment, you would be able to find the mass of the rod and the spring constant. And in the second experiment, you can find the mass of the rod as well. But it's kind of useless. You already found it. I mean, it could be useful to like compare the values and see what your error is. But you'd also have to do the calculation again and recalculate the slope by finding new data points and by measuring again. And then once you have that, you can draw the new line of best fit, calculate the new slope, and then do all that. So it's doing this once, basically, for doing this twice. And I'm ignoring all the physical limitations of measuring it twice, which oftentimes is the majority of the experiment, right? This kind of stuff is it's hard to do. So let's see, what's another experiment we could do? Because I totally thought there'd be more people joining. So feedback from people is always great. Let's see, physics 1 dynamics experiments. Okay. Measuring the coefficient of friction of something. So I actually I did this exact experiment that I'm about to show at a state fair one time. Like this exact experiment, I found the coefficient of kinetic friction between. And I'm not just a nerd doing this for fun. This is sort of physics assignment. We had to go to a field trip, or we not had to go. It was a choice, but I totally would go because a field trip is awesome, especially in a physics class. So we went there, and I measured the coefficient of friction between those carpets that they give you and the slide using the school experiment. I don't remember what the result I got, but it was cool. So what we're going to do is we're going to do the same thing with some assumptions, some physical assumptions. One thing to note about AP is they often won't give you these experiments that need physical assumptions because the assumptions you can make are so different. You can make one assumption here, one assumption there, and 2 people get completely different analytic solutions. But as long as the assumptions are right, the numbers they'll get will be similar. Analytic meaning an equation. Like for example, this is analytic right here. But when you're solving for numbers, it becomes a numerical value. So, but it's good to have that skill. And when you take engineering classes or physics classes or number-based chemistry classes, you're going to have to make those assumptions. And you can't make those assumptions because your stuff can be graded on an individual basis. But for AP, your stuff can't be graded on an individual basis, not for the AP exam. So what we're going to do is we're going to have an inclined plane with angle theta. There's a box up here. And this is also, I'm not going to use energy for this actually because you guys haven't learned energy yet, probably because my friend's university class is on energy, and I hope they're not behind you guys. And we're also going to set up a camera at this point to take pictures in time. So the camera is going to start timing when it hits here. until it travels here, some distance x, and this will take some time to travel. And using this small interval, we're going to approximate the speed that the block has at the end of the incline. So we need to find the acceleration first. So let's draw a free body diagram for the block. We have a normal force pointing perpendicular to the plane, force of gravity pointing down, and friction force, which is equal to mu times the normal force. Breaking stuff into components, just as usual. We have mg cosine theta and mg sine theta. You probably have these memorized, the mg cosine theta, mg sine theta down an incline, but it might, some people might not. I for sure don't ever. So we now have the acceleration down the incline. The acceleration down the incline, we'll denote that with the, we'll be fancy actually, we'll draw a triangle subscript. No, we won't. That takes too long. So we have acceleration down the incline is going to be mg sine theta minus the friction force, which is minus mu n. We have acceleration perpendicular to the incline, which is going to be 0, which we all know isn't really true if you've ever been on one of those fair slides. You sort of bounce up and down, but we'll assume that for the sake of this. And that's going to be n minus mg cosine theta. So this is equal to, because n is equal to mg cosine theta, this is equal to 0. Mg sine theta minus mu m g cosine theta. And this is not a, this is ma, and this is also ma. So these masses cancel out. So now you get the acceleration is equal to, we're going to factor out a g here. We get g sine theta minus mu cosine theta. So we now have something that we can use the kinematic equations with. We have Vf squared is equal to Vi squared plus 2AD. And the way we measured the angle was we measured the height of the slide and the length of the slide. So from here you can find the distance. It's just the square root of the sum of the squares by Pythagorean's theorem. So this is h squared plus l squared. So now this is equal to Vi squared. Actually, this quantity, Vi squared, is going to be equal to 0. You start at the top of the slide with no speed. So this is 2. The acceleration, which is g sine theta minus cosine theta, or minus mu cosine theta, times square root of h squared plus l squared. And there's some nice cancellations here. We have sine theta being opposite over hypotenuse. So we have 2g sine theta is opposite over hypotenuse, which is h over square root h squared plus l squared, minus mu cosine theta is adjacent over hypotenuse, which is l square root h squared plus l squared, times square root h squared plus l squared. So this square root, and this square root cancels. So now you have 2g h minus mu l, which I think is a much nicer expression than before. So we now have the final speed at the bottom of the incline. V at the bottom of the incline is going to be 2g times, or root 2g h minus mu l. And we're going to make some assumptions here. So we want the speed here, but how do we measure instantaneous speed? We're going to, for a small time interval right here, we're like, I did it in like a fifth of a second just by using slow-mo on my iPhone. So that means that the velocity at the bottom of the incline is approximately equal to x over t. Not exactly, this would be the average over this, but if you make t sufficiently small, it becomes the speed at the bottom of the incline. So now we have VIT is equal to x. Actually, we're not going to substitute that in yet. We'll substitute in x over t for this v. So we get x over t is equal to square root 2g h minus mu L. So now we have x is equal to time times square root 2g h minus mu L. And from here you can see that this doesn't depend on mass at all. Like at all. There's no mass dependence here, which is nice. So what are we gonna do? We can't graph mass. The only non-constant quantities here are x and t. But the whole point here was that we made t small enough so that t was about 0. So what we would do is we would graph x versus t, and we would get a linear line. That would look something like that. T versus x. We have to be careful here. T has to be small for this approximation to work, and this wouldn't be exactly linear because this equation isn't really true unless t is sufficiently small. So as t gets bigger, the area gets bigger. So it becomes less and less linear as t gets bigger. So you have to, this camera that's set up, I'm gonna draw the camera here. It would have to be, it's a really bad camera. This camera setup here would really have to, I'm gonna stop drawing the camera. This camera here would really have to be slow motion. And like for an iPhone, for example, if you have, you're given the frames per second in slow motion. You can look that up online. I think the normal recording is 30 frames per second. So the, let's say the slow-mo records at like 10 frames per second. So it normally records at 30 frames per second if it's not slow motion. But if it's slow motion, it records at 10 things per second. So the length of your video in slow motion, which would be like maybe like 3 seconds, you divide that by 3 because 30 frames per second over 10 frames per second is 3. So you divide that by 3 to see how many seconds you actually got. Or if the video is 3 seconds, you actually captured 9 seconds because you captured more time in slow motion. So from here, you'll get that the slope, this is again in the form of y equals mx plus b. This is the dependent variable, independent variable, and the slope. Slope is equal to square root 2g h minus mu L. So square root slope, we'll define this as Greek letter sigma, because sigma s slope. So we get sigma squared is equal to 2g times h minus mu L. Divide everything by 2g. Sigma squared divided by 2g is equal to h minus mu L. See, we'll continue working up here. Draw that arrow better. So now we have, we're subtracting h over. So we have sigma squared minus, or sigma squared over 2g. I'll make that neater. Sigma squared minus 2g, or over 2g minus h is equal to negative mu L, and we're going to divide both sides by negative L. So we'll get mu is equal to H over L minus sigma squared divided by 2GL. And this sigma meaning the slope of the graph. So a lot of these times you'll be given you'll be given the actual exact value, which is kind of funny because when you're thinking about like the exact value of spring constant is determined experimentally. So it's not really an exact value, it's just an experimental value that someone better at experimenting than you did. So for example, when you have these values, this is K1, let's say you're given an actual K value of 0.082. So we'll say the actual K1, we'll denote that actual. That's not a K to the power of actual, that's just another script. So we'll say the actual K1 is 0. We'll say my experiment sucked, and we'll go 0.13 newtons per meter. So when we're calculating the percent error, this is going to be equal to the actual minus theoretical divided by the theoretical, which is equal to, so the actual minus the theoretical, it's the absolute value, so you can flip the two as long as it's positive. 0.13 minus 0.0841 divided by the theoretical, which is 0.13. So theoretical means actual, so this would be more like measured actually. Measured divided by theoretical over theoretical, because this actual is not that actual. So we now have, and this is multiplied by 100%, because 100% is just 1, and you can multiply any quantity by 1 and still get out the same thing. So calculating this, we have 0.13 minus 0.0841 divided by 0.13, and this is a 35.3% error, which honestly, like, it's pretty bad. It's not awful though. I've gotten some really bad percent errors. My most recent physics lab, we measured black body radiation coming off of a tungsten wire. If that means nothing to you, don't worry about it. The radiation coming off of a tungsten wire, and we sort of went with that based on the black body radiation model, if you know what that is. But if you know what that is, you're probably not in physics 1. And we got like a 25% error, which isn't that bad, honestly. It's like a quantum mechanics experiment, so the system's really sensitive. So the general thing is, if you got an error, a percent error of less than 5%, that means you did the experiment like really freaking well. If you got somewhere between 5% and like 25%, so let's say 0.05, it's like greater than or equal to, between this and like 20%. We have 2 check marks for just how good you did. 3 check marks actually. This is pretty good. So this is really good. This is pretty good. We'll say 0.20. The error now between this 20% and this 50%. Nah. And if your error is over than 50%, you're not doing well. That means you probably did something wrong. I got a percent error of like 128% one time in a physics 1 lab, which wasn't fun. And for this one, again, it's kind of ironic with this kind of stuff, with this, this equation for mu, this relation for mu with all the other physical quantities. It's kind of ironic because mu can only be measured theoretically or experimentally. You could you could get down to the microscopic level of things with the quantum mechanics and all that, and try and calculate mu. But I imagine it's really awful and probably takes like a decade or so to perform on a computer. So this is performed via experiment, and this mu will always be experimental. So you compare it with pretty much an experimental value that someone calculated that's better than yours, and you take that as if it were a theoretical value, which it's not experimental. Just it's an experimental thing of somebody that is more experienced than you are. So again, like there's the same an error analysis here. Let's say the actual value of mu is say 0.3, and you measured the actual coefficient of friction to be 0.21, so 0.30 for 2 sig figs. The percent error is equal to what you got, the measured, minus the actual value, 0.30. Make that bigger because the one sort of like not the absolute value bar over the actual, and we should get a better value for this. 0.21 minus 0.3 divided by 0.3. Yeah, that's 30%. So as you can see here, like the actual difference was lesser than this difference, right? This is like 0.9, and this is smaller than that. So the actual difference, when we're looking at percent error, it measures more than difference, it measures relative difference. So for example, like if you can if your friend can throw a baseball at some speed of a baseball, but you can kick a soccer ball, hope no one European is watching, but you can kick a soccer ball at some speed, your friend's gonna throw the baseball faster, but you really have to look at like a relative measure of it. So let's compare them with the averages. Let's put them on a relative scale. The average speed of the baseball, or the speed of the baseball your friend can throw, divided by the average speed. That's what that bar means. A bar means average of A, which is, we'll say AVG. So you have to compare this with the average of what someone can kick a soccer ball with. And I imagine this being greater, just because the distribution of speed of a baseball is probably going to be more narrow, just because most people can throw a baseball pretty fast, but the fastest is like 100 at most, so there's only like a 30-mile-per-hour difference. Whereas this one, there's a big difference in how much people can kick a soccer ball. So the whole point of percent error is to look at things relative to one another and relative to how the rest of how the distribution of the quantity exists, which is very important because when you're measuring error, when you talk about error in this experiment, you're talking about two completely different quantities, right? Like here you were calculating a spring constant, but here you were calculating a coefficient of friction. So it wouldn't really make sense to just subtract the two and say, oh, look, this difference is bigger, because they're completely different quantities. It's almost literally like comparing apples and oranges. So you have to compare them to some relative scale, and that relative scale is percent error. That's not on the formula sheet. You're just going to have to memorize it. So percent error for some physical quantity, we'll call it, what are we gonna, some Greek letter, right? Of course we're gonna use a Greek letter. Lambda. So percent error for some value of lambda is going to be the absolute value of the actual value of lambda minus what you measured. So measured divided by the actual value. This is a very important equation to memorize for the AP exam, because it's not in the equation sheet, because it's kind of seen as one of those things that's like Oh yeah, that's obvious. That's an obvious mathematical equation. So like, it's not really worth putting on the equation sheet because it's like it would be like defining multiplication on the equation sheet, I think, in a similar sense, but it's not as obvious as someone who's never seen it before. Just like multiplication isn't obvious to an elementary school kid that's never seen it before and has only seen addition. So it's the same reason there. So Bingo's still here. I don't know if he's he or she is still in the tab, but I'm gonna go ahead and end it here just because there's no one here to ask questions. So if you're watching the replay, my Instagram is at jjeffries12. 12 is my old soccer number when I used to play league soccer. You can DM me and ask me a question about your physics homework, or your chem homework, or your calc homework, or your pre-cal homework, maybe your stats homework if I remembered it enough. Pretty much anything STEM, I'll try and answer. Biology is going to be the worst one, especially now. Maybe next year it won't be that bad because that's when my biology classes actually start. So you can DM me anytime, ask any questions. I'll respond whenever I can, and I'll get to you as soon as I can if you want to ask questions. So if you're watching the replay, whatever time of day it is, have a good day, sleep well, have a good morning. Whenever you're watching it, take it easy.